What specific problem does DIFFUSEARCH aim to solve in the context of chess-playing AI, and how does it differ from conventional explicit search methods like MCTS?
DIFFUSEARCH aims to solve the problem of improving next token or action prediction in chess-playing AI by enabling the policy model to predict and utilize future states without relying on explicit search methods like Monte Carlo tree search, MCTS. Unlike conventional explicit search methods, which require extensive simulations and can accumulate errors due to inaccuracies in the value model, DIFFUSEARCH employs a discrete diffusion modeling approach that internalizes a world model directly within the policy. This allows DIFFUSEARCH to perform implicit searches by leveraging future representations through a bidirectional self-attention mechanism, enhancing decision-making without the computational overhead associated with MCTS. The results demonstrate that DIFFUSEARCH outperforms both one-step policies and MCTS-enhanced policies in terms of action accuracy and puzzle-solving capabilities, showcasing its effectiveness in long-term planning. Overall, DIFFUSEARCH represents a significant shift from traditional search algorithms by integrating future awareness directly into the policy framework.
How does the proposed DIFFUSEARCH algorithm work? Please provide a step-by-step breakdown of its methodology, specifically detailing the role of discrete diffusion modeling and the bidirectional self-attention mechanism.
The DIFFUSEARCH algorithm operates by integrating discrete diffusion modeling with a bidirectional self-attention mechanism to enhance future action prediction without relying on explicit search during inference. Firstly, it utilizes discrete diffusion models to generate future representations through a multi-step generative process, where the forward process corrupts the original data into noisy latent variables, and the learned backward process denoises these variables back to the data distribution. Secondly, the algorithm employs a bidirectional self-attention mechanism that allows the model to consider both past and future information simultaneously, facilitating the iterative refinement of action predictions based on future states and actions. During training, the model is supervised using a dataset constructed from optimal moves suggested by Stockfish, enabling it to learn the dynamics of the game effectively. Finally, during inference, DIFFUSEARCH predicts actions by sampling from the trained model, optimizing the action selection process without the need for extensive search, thus achieving improved performance in tasks like chess.
Can you provide a simple illustrative example that walks through the main steps of the DIFFUSEARCH algorithm, highlighting how it utilizes future predictions to enhance decision-making?
The DIFFUSEARCH algorithm enhances decision-making by predicting future states and actions through a multi-step diffusion process. For instance, consider a chess scenario where the current state is represented as S_0. The algorithm first generates a sequence of future states and actions, such as S_1 and A_1, by utilizing the internal bidirectional self-attention mechanism to capture interactions between the current state and potential future moves. It then refines the prediction of the next action, A_0, by considering these future representations, effectively allowing the model to foresee the consequences of its actions. During inference, instead of performing explicit search like MCTS, DIFFUSEARCH evaluates the joint probability P_theta A_I, Z_I, S_I, to select the best action and future state, thus streamlining the decision-making process. This approach not only improves action accuracy, but also enhances the model's ability to plan strategically over multiple moves, as evidenced by its superior performance in chess tasks compared to traditional methods.
What are the key theoretical advantages of DIFFUSEARCH over the MCTS enhanced policy, particularly in terms of action accuracy and long-term planning capabilities?
DIFFUSEARCH offers significant theoretical advantages over the MCTS enhanced policy particularly in action accuracy and long-term planning capabilities. Firstly, DIFFUSEARCH outperforms the MCTS enhanced policy by achieving a 14% increase in action accuracy, demonstrating its superior ability to predict the next action effectively by leveraging future information through its internalized world model. Additionally, it shows a remarkable 30% improvement in puzzle-solving capabilities compared to the MCTS enhanced policy, indicating enhanced long-term planning. The implicit search mechanism of DIFFUSEARCH, which utilizes a multi-step diffusion process, allows it to refine predictions iteratively, without the compounding errors associated with repeated value model invocations in MCTS. Furthermore, DIFFUSEARCH's ability to maintain a higher LO rating, 540 points more, underscores its effectiveness in strategic decision-making, showcasing its potential to substitute explicit search methods with a learned model that inherently understands future dynamics.
How was the DIFFUSEARCH method validated in experiments, and which datasets, benchmarks, or performance metrics were used to demonstrate its effectiveness?
The DIFFUSEARCH method was validated through extensive experiments focused on chess-playing tasks, utilizing a dataset constructed from games recorded in February 2023, with up to 100,000 games for scaling behavior analysis. The performance of DIFFUSEARCH was benchmarked against several models, including the SA-SV and SAV models, as well as an MCTS enhanced policy, with metrics such as action accuracy, puzzle accuracy, and tournament LO ratings being employed to assess effectiveness. Specifically, DIFFUSEARCH outperformed the one-step policy by 19.2% in action accuracy and the MCTS enhanced policy by 14%, while also achieving a 30% increase in puzzle-solving capabilities and a 540 LO rating improvement. The experiments demonstrated that DIFFUSEARCH's implicit search approach significantly enhances long-term planning and decision-making compared to traditional explicit search methods. Additionally, the model's performance was analyzed through various future paradigms and training methodologies, confirming its superior predictive capabilities in chess scenarios.
What limitations or challenges does DIFFUSEARCH have, especially regarding its applicability in scenarios beyond chess, and what future work is suggested to overcome these drawbacks?
DIFFUSEARCH faces limitations primarily in its reliance on the quality of future predictions, which can diminish as the horizon increases, leading to reduced accuracy in subsequent actions and states. This challenge is particularly evident in complex environments beyond chess, where the dynamics may not be as predictable or structured, potentially resulting in compounding errors similar to those seen in traditional world models. The paper suggests that future work should focus on enhancing the model's ability to generalize to diverse tasks by improving the training data quality and quantity, as well as exploring self-play training to better capture the intricacies of various environments. Additionally, the authors indicate that further research is needed to refine the integration of future representations and to assess the model's performance in more dynamic and less deterministic settings. Overall, addressing these challenges will be crucial for DIFFUSEARCH's applicability in broader AI problem-solving contexts.